At this time tomorrow, I'll be up in the area. Scholarships.
All right, so yesterday we were looking at the product rule in terms of analyzing graphical information to help us get pieces or number values to evaluate a derivative or find a derivative. We're going to do similar examples today, but instead of having graphs to find information from, we're going to have a table. So it's just a different type of information given, but you have to realize how to analyze it. So let's check out some of these questions. They're going to be very similar questions just like we've been doing so far. It's just we may have to use a product rule because that's kind of the focus of this section. All right, so take a look at the first one. Estimate the value of f prime, okay, the derivative, at the x location of 3.5. We're trying to figure out the slope of the tangent line at 3.5. How might you guys want to estimate the value of the derivative at 3.5? We might not be able to find it exactly. What do you think, Braden?
Just in between the values of 4 and 3.
4 and 3. Okay, so 3.5 is in between these x values. So then which other values from the table should we be looking at? Oh, there's a lot of other numbers there. So the derivative, the slope of the tangent line at 3.5 is roughly what? How'd you get that? Okay, so what's a little tricky, because we do have all these numbers, we know that the derivative at 3 is -4, and we know the derivative at 4 is 2, so we might be able to reason through that the derivative at 3.5 is somewhere in between there. Okay, -1 is kind of the middle ground, but that might not necessarily be true, okay? I know that we have those pieces, but just because this slope is -4 and this slope is 2 doesn't mean exactly between these values is the exact middle of those, okay? So we're not necessarily looking here to estimate a derivative. We gotta look somewhere else. What do you think? Yeah. All right, so slope of secant line. Okay, so I'm going to draw this picture again. I hope it kind of brings back a memory. If we are trying to estimate the slope of a tangent line, okay, a derivative, maybe we can pick a point before that point and after that point and calculate the slope of the secant line. Does that drawing look familiar? Okay, this is always in relation to the graph of f, okay, an original function. So if we're focusing on 4 and 3 as the x locations, we got to focus on 1 and -2 from those y locations on the original graph. So slope of secant line on f of x from the x values of 3 to 4. So let's go ahead and calculate the slope between those 2 points. Okay, old school slope, like from Algebra 1, difference of y's over difference of x's. So our y values are -2 and 1. Okay, we'll subtract those. And then their respective x's are 3 and 4. So we'll subtract those. Looks like we'll get -3 over -1, which is 3. Okay, so roughly, approximately, The slope of the tangent line at 3.5 is 3. Notice how that's kind of contradicting what a lot of students think it should be, okay? Some of you might look at the derivative like Ryan did, okay? Believe me, people do this all the time. You think that if the slope is -4 at this x location and 2 at this x location, the derivatives in between those have to be between -4 and 2 as well. But notice how this one isn't. Okay, even though 3.5 is between those x values, the slope value is not necessarily between the slope values at those points. Okay, so it can get a little tricky, but it's always in relation to the original function, the original graph. All right, let's go ahead and check out another one. If q of x is this equation, what is the value of the derivative of q specifically at 4? Okay, let's go ahead and try to tackle the derivative of the q equation. We don't really have equations per se, like polynomials or trig functions or whatever, to find the derivative of. We have function notation. So how might we represent the derivative of f in function notation wise? Yeah? F prime. So if the derivative of f of x we say is f prime, then the derivative of 2f of x would just be 2f prime. Okay, those coefficients out front, you can kind of just keep them. It's just a constant multiplier. We then have to subtract the derivative of g, which we can represent as g prime, and that 4 is a coefficient, a constant multiplier, so we'll keep it. So there's the general derivative for q. They specifically want us to figure out the derivative or slope at 4. So let's go ahead and plug in 4 and for all of these x's. Based off the table, can we fill in some values? For instance, do we know the value of f prime of 4? Do we know the value of g prime of 4? Can you find those from the table? Can you get 2 and -3? Okay, so looks like we have 4 plus 12, which would be 16. All right. Haven't really had to use a product rule just yet. All right, let's check out the next one. If p of x is this equation, what is the value of the derivative of p at 3? Okay, so very similar to the last one we did. We're going to try to figure out the derivative equation, and then in this case we'll plug in 3, whereas the last case we plugged in 4. So let's take a look at the p equation. We have -2 times f of x times g of x. So how might you want to find a derivative of that function? Let's see, the -2 is a constant multiplier, okay, that coefficient, so we'll keep it. But how can you figure out the derivative of f of x times g of x? Yeah?
You could use the 1d2, 2d1 and plug in the values.
There we go. Okay, product rule. You're multiplying two functions together, so we're going to go through 1d2 plus 2d1. F of x is your first function, and then g prime would be d2. We then have to add 2, which was the g of x function, times d1, which would be f prime. Do you guys notice how I use brackets there? Okay, because when you find the derivative, it changes into 2 terms, and if you have that multiplier out front, you have to think about distributing it to those 2 terms. A little tricky. Okay, so if that's our derivative, let's go ahead and plug in 3, and we'll see what we get. Okay, if you were to plug in 3 into the f table, looks like you get -2. If you plug in 3 into the g prime table, looks like you'll get +2. If you plug in 3 into the g table, looks like -3. And if you plug in 3 into the f prime table, looks like -4. All right, so cleaning it up, we have -4 plus 12, which is 8, times that -2 coefficient out front, so we got -16. We hanging in there? Okay, let's check out the next one. Find the equation of a tangent line. What do we need to know? Point and slope. All right, so point comes from original function, which we have. Slope comes from derivative, which we should be able to figure out. So let's go ahead and check this out. If we were to calculate or find v prime, okay, the derivative of that function, how might you want to do that? We have x cubed times f. You're multiplying two functions together, so our derivative shortcut would have to involve the product rule. So we have 1 d2 plus 2 d1. So original equation for point, derivative equation for slope. Let's go ahead and plug in the x value of -1, that's our tangent location, to figure out those two values. So if we were to plug in -1 into the original equation, we need -1 cubed times f of -1. -1 cubed is -1. What about f of -1? Based off the table? Looks like you get 2. All right, so our point value, or y value, is -2. Let's go ahead and tackle the slope. We'll plug in -1 into the derivative we found. All right, so -1 cubed is -1. We then have to figure out what f prime at -1 is. And then we'll add f of -1, and -1 squared is +1 times 3 is 3, so we'll have to multiply that by 3. So based off the table, f prime of -1 is 1, and f of -1 looks like 2. So -1 plus 6 gives us 5. Okay, so you know your point, you know your slope, write your equation. Y minus the point equals the slope times x minus your tangent spot. Do you guys think you could have done that one? I like the head nods, maybe. Nah, iffy. Believe me, we're going to have a lot more examples of these. Okay, they'll start to sink in eventually. All right, let's try a good one at the bottom. If k of x is that equation, what is the value of the derivative of k at the x value of 3? Okay, so notice how the k equation is comprised of one piece multiplied by another. Okay, maybe we can go through that product rule to do or figure out the derivative. You could also expand this if you wanted to. Do we have a preference on which way we tackle it? Remember, if we're multiplying polynomials together, which essentially these are, you could expand them first. What do you want to do? You want to expand, or do you want to product rule it? Speak now, forever hold your peace. You want to expand? Okay. So if we go through FOIL, this would become 6 f of x minus 2 f of x g of x. And then plus 9 minus 3 g of x. All right, so let's go ahead and tackle the derivative. Okay, one term at a time, one piece or section at a time. So look at your first term here. The 6 is a constant multiplier coefficient, so we'll keep it. How do you want to represent the derivative of f? Maybe we'll write f prime. Okay. If you look at the, bless you, if you look at the next term, we have negative 2 or minus 2 as that coefficient, so we'll keep it. But then how do you want to find the derivative of f of x times g of x? Okay, we can't just write f prime g prime. Remember that was Lily or Lizzie or whatever her name was? Unfortunately, it doesn't work that way. Okay, we're multiplying two things together, so we're going to have to go through that product rule. So we tried to work around it initially. Okay, instead of using the product rule at the top, we decided to expand it, but in doing so, it looks like we're going to have to do a product rule anyway. Maybe it's just not as intense as the one at the very beginning would have been. So we have 1 d2 plus 2 d1 If we move on to the next term, what's the derivative of 9? The derivative of a constant? 0. Good. Okay, so we'll just ignore that and we'll move on to the next term. Negative 3 is a coefficient, a constant multiplier. So then how can we figure out the derivative of just g? We can use the g prime notation. All right, so there's our derivative. We worked through one term at a time. Let's go ahead now and we'll plug in 3 to see what we get. So if you were to plug in 3 into the f prime table at the top, looks like you get negative 4. Let's see, 3 into the f table at the top, you get negative 2. 3 into the g prime table at the top, you get positive 2. 3 into the g table at the top, we'll get negative 3. 3 into the f prime table, we'll get negative 4. And then lastly, 3 into the g prime table, we'll get negative 3. Okay, so all the values are able to be substituted in based off the information from the table. We just need to calculate what the heck we get out. Let's see, negative 24 minus 2 times negative 4 plus 12, that'd be 8. And then plus 9. Negative 24 minus 16 plus 9. Is that one wrong?
Yeah.
Oh, I looked at the G table. My bad. So this would be minus 6. Thank you. So negative 24 minus 16 minus 6. Negative 46. Is that right?
Yeah.
Yeah? Sound good? All right. Checks out. All right, if you would have done product rule initially, okay, 1d2 plus 2d1, you still should have gotten the same thing. Okay, so you do have options if they're polynomials. You can expand and then do a derivative, or you can do a derivative and then expand, aka simplify. Okay, we're going to see a lot more examples of these tables and graphs when we start our next section today. Okay, so the section we just finished is our product rule. That's our shortcut that we have for when we're multiplying two functions together. Our next section on page 149 we're going to talk about the quotient rule, which what do you think our shortcut for this one would entail? Quotient means division. Okay, so what if we're dividing two functions together? How do we have a shortcut to figure out the derivative of that type of equation? Okay, so let's check it out. Let's do something that we already know how to do and then make a connection perhaps to our quotient rule. So we're going to rewrite this function as a polynomial. How might you guys want to do that? How can we turn a fraction into a polynomial? What's special about that guy in the bottom? Remember, this means something different in health class, right? Okay, so if you have a single term denominator, you can break up the numerator, okay, each individual term in the numerator with that single term denominator. So if you were to do 2x cubed divided by x squared, 2 x's would cancel, so you're just left with 1x. If you moved on to the next term, 3x squared divided by x squared, both x's would cancel, so you're just left with that minus 3, or negative 3. And then for the last term, you're strictly left with 2 over x squared. But if we want it in polynomial form, we don't want any fractions left over. So instead of having that x squared left in the denominator, let's go ahead and move it up to the numerator, and that would change the power to a negative because we moved it. All right, so up to this point, the only way we've discussed turning a fraction into a polynomial is if you have a single term denominator. You can break up each individual numerator term. Can we calculate the derivative now that it's in polynomial form? We can use our power rule shortcut. We have x's to powers all the way through. So it looks like 2 minus 4x to the negative third. Can we rewrite that? Instead of a negative power, let's make it positive. Okay, we'll move it to the bottom of its individual term. Not both of them, okay, because notice how the x is only attached to the 4. It's not attached to the 2 as well. Can we turn that into a single fraction? Can we actually go through the subtraction? 2 minus this fraction? You need to get a common denominator, so what would you have to multiply the first fraction by on top and bottom? How can we get a 1 and an x cubed to be exactly the same? We got to multiply, right, we got to multiply this first fraction by x cubed on top and bottom. So we'd have a 2x cubed minus the 4, and we'll keep that new common denominator of x cubed. Okay, if you wanted to check your work, notice how you have a single term denominator. If you were to break it up, you would get this, okay, what you originally had before. So you can check your work. So technically all three of these represent a derivative. They just all look different. Okay, now that's nice. We can attack fractions, finding their derivatives that way, okay, if we have a single term denominator. But what if we didn't have a single term denominator? For instance, if you look at the function at the very bottom of that page, it says 2x minus 1 over x plus 3. That's not a single term denominator. You have two terms down there. You have an x and a 3. So unfortunately, you cannot break it up like we did before. So there must be some shortcut, some other way we can find derivatives of fractions, and that's what this quotient rule is going to go through us, or give us a method to do. So we're going to say if we have some function defined as the division of two things, then the derivative of that function, okay, in this case at h of x, do you think it's as easy as just doing the derivative of the top divided by the derivative of the bottom? You would hope, right? Okay, but unfortunately it's not. Remember how the product rule, it was not as simple as just the derivative of the first times the derivative of the second? Okay, Lily or Lillian, Lizzie, whatever her name was incorrect. The same thing's going on with the quotient rule. It's not as easy as just the derivative of the top over the derivative of the bottom. Okay, so what I'm going to do is I'm going to write this down, what the actual shortcut is. It might not look like a shortcut to you guys, but we're going to discuss it. Okay? I want to see if you can understand what this is exactly telling us. Now. I know it looks like a lot, but I'm going to give you another little phrase to help you remember this one by. Okay, we'll write that at the top. Can you describe what this derivative process is for the quotient rule? If this is your original function, okay, sum top divided by sum bottom, how would you describe the derivative based off the notation? Like, what would you say to someone if they asked, how do you find the derivative of a fraction? What would you say to them? I doubt you would say g of x times f prime of x minus f of x times g prime of x over g of x squared. Can you describe it in words? What do you think? Yeah.
Well, the top is like 1, 2, 1, it's minus. I don't know.
Okay, so it's very similar to the product rule, right? 1d2, but instead of plus, we have minus 2d1. Okay, so maybe we're talking about the first fraction being the top, or sorry, the first function being the top, and then the bottom fraction being the 2. Maybe you can think about it that way. That's one way to do it. I don't want you guys to mix up the product rule and quotient rule. So instead of doing the 1 and the 2 idea, like we did before, we're going to do what I might call the high function, meaning the top function, and then the low function, meaning the bottom. Okay? So our little phrase, okay, if you look at it, we're going to have low d high, right, the derivative of the top, minus high d low, the derivative of the bottom, right, all over low squared, or bottom squared. So my phrase you're going to hear me say all the time, low d high minus high d low, square the bottom, and away we go. Okay? Low d high minus high d low, square the bottom, and away we go. Little rhyme. Okay? So we'll write that at the top. Low d high minus high d low square bottom, and away we go. Okay, if you want to make it rhyme. Low d high minus high d low, square the bottom, and away we go. So to figure out, using a shortcut, okay, the derivative of a fraction, it's still going to be a fraction, notice that, but we have the low d high minus high d low part up top, and the squaring the bottom remains in the bottom. Okay, so we're going to practice this quotient rule, this derivative shortcut for fractions. Let's go ahead and try to use the same equation from the top. Okay, we already know what the derivative of this should be. Okay, we found that all the way at the top. Let's try to apply the quotient rule though. Okay, maybe you didn't want to simplify it first. Maybe you wanted to go straight to quotient. Let's see if we can get the same thing. Okay, so low d high minus high d low, square the bottom, and away we go. So our low function is x squared. We then have to multiply by d high, or the derivative of the top. Can we see how that would be 6x squared minus 6x? Okay, so low d high minus high, and then d low, the derivative of the bottom, so that would be 2x. Okay, and that's all over the bottom squared. Okay, so that's what the initial quotient rule derivative shortcut gives us, but we're trying to check, does it match what we know it should be? Okay, so our goal is to perhaps get this 2x cubed minus 4 all over x cubed, okay, like we found before. So eventually this craziness is going to simplify to that. Let's see if we can actually do that. So maybe we can start to expand some of those parentheses, okay, get rid of those or distribute in those values. We would have a 6x to the 4th minus a 6x cubed minus 4x to the 4th plus 6x cubed minus 4x all over. And then what about x squared squared? X squared times itself. Okay, another x squared. What would our power be? X to the 4th. Okay. Let's see, if we combine some like terms, 6x to the 4th minus 2x, or sorry, 4x to the 4th would give us a 2x to the 4th. We have a negative 6x cubed plus a 6x cubed, so those are actually going to go away. And then we have a minus 4x. Anything else going to happen? You do have that single term denominator, so you could break it up if you wanted to. Okay, notice how initially the x to the 4th would cancel, so you'd be left with that 2. And then only one x would cancel for the other term, and you would still have 3 left in the bottom. Do you see how that matches the similar derivative we had up top? Right? Okay, so instead of using polynomial form, okay, simplifying first and then finding a derivative, you could use a quotient rule. But just like the product rule, okay, sometimes you have no choice but to use the product rule, and we're going to see that in some cases. Okay, so for polynomials, again, you have options, but specifically the only option you have for a fraction is if you have a single term denominator. That's the only way you can get around using the quotient rule. All right, so let's take a look at an example where the quotient rule is the only option we have. Okay, the next example at the bottom, if you take a look at that function, we don't have a single term denominator. So there's no way around to rewrite that fraction. If we're going to find the derivative, we have no choice but to use the quotient rule. Now I know the directions say find the equation of the tangent line. Okay, we're used to that, we'll get there. But let's just go ahead and practice our quotient rule. Okay, low d high minus high d low, square the bottom, and away we go. All right, so low, we would have x plus 3. What about d high, the derivative of the top? Two, good, okay. There's low d high. We now need to subtract the top function, okay. That's the high part. Now we have to multiply by d low. What's the derivative of the bottom? Okay, Okay, just 1, but you don't have to write it if you don't want to, because multiplying by 1 doesn't really change anything. And that's all over the bottom, x plus 3 squared. All right, let's go ahead and clean it up, okay? Or at least the tops. We can clean up the tops. The bottom part already looks kind of nice. It's x plus 3 squared. You don't necessarily have to write it twice and go through a FOIL process. Okay, so we'll leave the bottom by itself the way it is. But we can clean up all those parentheses up top. If we distribute in the 2, and then distribute in the 1 and the negative, looks like the 2 x's are actually going to cancel, so that's nice for us. And we have 7 over x plus 3. So notice how the initial derivative looks kind of complicated. You have all these different quantities and parentheses being multiplied together, but you can always simplify it to something a little bit more nice to use. Okay, so now that we have the derivative, let's go ahead and tackle this equation of the tangent line. We got to figure out a point, and we got to figure out a slope. It looks like our tangent point is -2. So if you were to plug in -2 into the original, let's see, we'd have -4 minus 1, we'd have -5 over 1, which is just -5. And then if we plug -2 into the derivative, let's see, -2 plus 3 is 1, 1 squared is 1, 7 divided by 1 is just 7. Okay, so point, slope, put them together, write your equation. Y plus 5 equals 7 times x plus 2. Do you guys notice how we're still doing the same types of questions? Okay, we're just adding techniques to help us find the derivative. Okay, so the questions aren't really going to change. It's the method or the process in which you figure out your information. Okay, specifically that slope value, because that comes from the derivative. Okay, so we have 2 new shortcuts so far. We have the product rule, 1d2 plus 2d1, and now we have the quotient rule. Low d high minus high d low, square the bottom, and away we go. Okay, those are going to be 2 big ones from this unit. Are we doing okay with those 2? Okay, we would rather do those than the whole limit process, right? Okay, so I know that the quotient rule is a little bit more involved than the product rule, but it's still better than doing the limit. Okay, we're going to stop there for today. Next week, we're going to check out some more trig derivatives. Okay, we already know what the derivative of sine and cosine are, but what about the other trig ones? Okay, we'll check those out next week.